Hello viewers, and welcome once again. We are still under logic, Christ Almighty God's algebra. In our last tutorial, we treated law of constants by conjunctive statement. Today we are going to treat law of constants by disjunctive statement. Let us start. Law of constants. P or T is equal to T. This is a typical example of law of constants by disjunctive statement. Why is it called law of constants by disjunctive statement? It's because of this or connective that combines P and T together as a compound statement called disjunctive statement. But the reason that this statement is disjunctive statement, that's why it's called law of constants by disjunctive statement. So let us prove the statement P or T is equal to T. Proof. Suppose P or T is equal to T. Suppose P or T is equal to T. We assume that the statement is true. That means P or T is equal to T. If you look at this statement, you will find out that P or T equal to T is a logical equivalent. In the sense that whenever the left hand side of the equation is true, also the right hand side equation is also true. Whenever the right hand equation is false, also the left hand side equation is also false. We say it's logical equivalent. But in this case, the relation of P or T is constant, is always TT throughout. There's no variable of T and F, always truth, always T. Also, here is also constant, always T. So, we say that it's equivalent because whenever P or T is T, also T is also T. Whenever T is T, also P or T is also T. We say is what? Is logical equivalent. Since it's logical equivalent, we can transform it to biconditional statement. If and only if P or T, if and only if T, we have now transformed it to biconditional statement. That is, whenever the left equivalent is true, also the right equivalent is also true. In the same vein, whenever the equivalent is false, but there's no falsity in the T, this topology always T. Also here is also always T. So whenever this T is T, that means the right equivalent is T, also the equivalent is also T. Whenever the equivalent is T, also the equivalent is also T. So if you write this statement, that's not possible getting falsity, always truth. We say that the statement is tautology. Is tautology being justified by logical equivalent. Being justified by logical equivalent. Being justified by logical equivalent. If and only if P, since this statement is tautology, I mean this P or T, if and only if T is tautology, we can also transform it to biconditional statement. Since this biconditional is tautology, we can also transform it to conditional statement and it will preserve tautology. That means P or T implies T. You find out that whenever the antecedent is true, also the consequent must also be true. So if you statement that was getting positive, always truth. You say statement is tautology. Statement is tautology. Being justified by logical implication. Biological implication. Now, since this conditional statement is tautology, that means P or T implies this tautology. We then deduce that P or T exists. We then deduce that P or T exists because P or T is proper implication of T. Since P or T exists, we say that P or T is logical implication of T, the consequence. Say if and only if P or T is logical implication of T. Since P or T is logical implication of T is true, also this must also be true. If and only if P or T is equal to P or T. That means it is true that P or T, that is logical implication, is equal to itself. If it is equal to itself, it is what? Logical equivalent. In the sense that whenever P or T are the left hand side equation is true, also P or T at the right side equation is also true. Whenever P or T at the right equation is true, also P or T at the left hand equation is also true. We say it's logical equivalent. So it is true that P or T is equal to P or T, being justified by identity. Being justified by identity, that means the sameness. Being justified by identity. Now, since P or T equals P or T is true, also must also be true. If and only if P or T is equal to P or, now this T is equal to not P or P, not P or P. Let's say P or not P, the same thing, is equal to P or not P. By law of complement, T is equal to P or not P. Bracket P or not P. Being justified by law of complement. Law of complement. being justified by law of complement. Say if and only if and only if P or T is equal to P or P or T. You see that you have now associated P or T by law of associativity. This P or bracket P or not P is equal to bracket P or T by law of associativity. They are is equivalent to this is equivalent to the other one. So by law of associativity, by law of associativity, sorry, not P. It is sorry, this is not P. Is not P. So it's not T, not P. Is by law of associativity, you should take this P or P. We continue. So if and only if and only if P or T is equal to, you see that this P or P is equal to P by law of idempotent, is equal to P or not P by law of idempotent. By law of idempotent. That means P or P is equal to P by law of idempotent. That means this P or P is equal to P by law of idempotent. If and only if P or T is equal to T. That means P or T is equal to P or not P is equal to T by law of complement. P or not P is equal to T by law of complement. Law of complement. We have now proved that P or T is equal to T. Since I have now proved that P or T is equal to T, we then conclude, say, thus P or T is equal to T. Since the statement is logical equivalent, that means statement is logical equivalent, we are going to prove the converse, that also converse holds, so that by the rule of causality we then establish that law that P or T is equal to T. Conversely, T is equal to P or T. T is equal to P or T. You will see that this P or T is at the let's say equation here has now become P or T at the right hand equation here. T at the right hand equation here has now become T at the left hand equation here. That means it is converse. We are going to prove this converse so that we establish that by the principle of disparity that P or T is equal to T is law of constant by disjunctive statement. So suppose T is equal to P or T. We assume that the statement is true. That means T is equal to P or T. Since statement is logical equivalent, that means whenever the left hand side of the equation is true, also the right equation is also true. Whenever the right equation is true, also the left hand equation is also true. So we say that it's logical equivalent. So since it's logical equivalent, we can transform it to biconditional statement. It's if and only if T, if and only if P or T. T, if and only if P or T. If you see that whenever the left equivalent is true, also the right equivalent is also true. Whenever the equivalent is true, also the left equivalent is also true. So if you write this statement, there's no possibility of getting positive, always truth. You say the statement is tautology. Is tautology being justified by logical equivalent? Being justified by logical equivalent. Being justified by logical equivalent. So if and only if. Now, since this statement, this partial statement is tautology, that means T, if and only if P or T is tautology, we can also transform it to conditional statement and it will still preserve tautology. That means T implies P or T. We see that whenever the antecedent is true, also the consequence is also true. If that is the case, if you validate the statement that was negative positive, always truth. The statement is tautology. Statement is tautology. Is tautology being justified by logical implication. Being justified by logical implication. Being justified by logical implication. We go to this side. Say, if and only if, since this statement T implies P or T is tautology, we then deduce that T exists because T is proper implication of P or T. And if T exists, we then say that T is logical implication of P or T. T is logical implication of P or T. So logical implication of P or T. Since T is logical implication of P or T is true, also this must also be true. You say if and only if T is equal to T. That means the logical implication is equal to itself. And if logical implication is equal to itself, it is logical equivalent. It is true that it is logical equivalent. In the sense that whenever T is T, at the left hand side equation is T. Also T at the right hand side is also T. Whenever T, since T at the right hand side is T, so also T at the right hand side is also T. So you say that it's logical equivalent, being justified by identity, the sameness. Being justified by identity. Being justified by identity. If and only if T is equal to P or not P. That means this T is equal to P or not P by law of complement. So by law of complement, this T is equal to P or not P. That's why it's displayed with P or not P. Being justified by law of complement. Being justified by law of complement. If and only if T is equal to P or let's say P or P or not P. This P is equal to P or P. By law of complement, P is equal to P or P. I mean, by law of idempotent. By law of idempotent, P is equal to P or P. That's why I split this P with P or P. Being justified by law of idempotent. If and only if T is equal to P or bracket P or not P. See that this P or bracket P or P or not P is equal to P or bracket P or not P by law of associativity. By law of associativity. By law of associativity. Also, if and only if T is equal to P or T, you see that this P or not P is equal to T by law of complement. So that's why split P or not P with T. So B plus phi by law of complement. You go to the side. We have now proved the converse. That means T is equal to P or T. We have now proved the converse of this. P or not P or T equal to T. That means T equal to P or T. P or T equal to T. T equal to P or T. That means the converse. We then conclude, say thus T is equal to P or T. Since I have proved the converse by the principle of isoscelerity, we then establish that P or T is equal to T. Is law of constant by disjunctive statement. Therefore, P or T is equal to T. We have now proved that law of constant by disjunctive statement exists. So, at this juncture, we will draw our curtain. Thank you, viewers.